Can you see my screen?
Yes.
Okay, so thank you for the introduction. I also want to thank Professor Daniel and Professor Sylvia for organizing this session. So today I want to talk about homogenization of non-dilute suspension of a viscous fluid with magnetic particles. So this is a joint work with Julia Go from SF and Sylvia Zimmerman from Colgate University. So our problem comes from the model of magnetorheological fluids. So first, let me remind you something about them. Okay. So magnetorheological fluids are colloids consisting of a large number of fairly small magnetizable particles which are suspended in a carrier fluid. Therefore, we can control the movement of those fluids by means of magnetic fields. A typical example of magnetorheological fluids is ferrofluid. So as you can see in the picture, if you put a magnet underneath the glass, then the ferrofluid on the top will form a regular pattern of peaks and valley. So ferrofluid was invented by NASA in 1963 in order to create a liquid rocket fuel that could be drawn toward a fuel pump in the weightless environment by applying a magnetic field. Recently, those fluids found more interesting application. For example, in drug targeting or molecular communication system. For example, in magnetic drug targeting, the magnetic nanoparticles are supposed to carry the drug molecules which are adhered to their surface through the vascular system to a precise defined location in the human body. So this is an interesting approach for tumor therapy. So another application is molecular communication system. So in a very small fluidic communication system that electromagnetic waves can no longer be used. So magnetic nanoparticles are used as massive carriers. Here the magnetic fields are expected to accelerate the transport of the magnetic nanoparticles, which used as a massive carrier. And this way to sharpen the signal by diminishing the diffusive effect. So in general, the most important application of those fluids come from the fact that we can control their viscosity, their effective viscosity with an external applied magnetic field. So for example, as you can see in the picture, magnetorheological fluid can even solidify in the presence of a magnetic field. And so in order to control the fluid effectively, we need to do some mathematical model. So usually there are two approaches. So the first one is used by some physicists and engineers. Okay. So the first model was derived by Nuringer and Rosenway in 1964. And later we also have a series of numerical simulation published in 2008 from Kang and his colleague. However, those models doesn't lead to a straightforward control over the effective property. So the question is, can we find a model depending explicitly on the microstructure and the properties of the constituents? So if we assume that the underlying microstructure of heterogeneity is periodic, then we can apply the mathematical theory of homogenization. So this approach is used by Levy and Valencia and also Lika and Vanescu. So let me mention the first paper by Levy and Valencia, which is published in 1983. So in this paper, they consider this problem in the action of magnetic field. And 5 years later, they have another paper with the assumption that the magnetization doesn't depend on a small scale. And recently, we have a paper by Nika and Vanescu. So in this paper, Nika and Vanescu provide the, an asymptotic analysis and simulation for this problem, where they allow the magnetic fields depend on small scale. So, however, those papers only provide for us analysis. So our aim is to justify those analyses mathematically. I also want to mention a similar work recently in electric by Frankfurt, Gloria, and Lopez Pamay. So their model is similar to our one, but they consider the coupling between electric field and the electric material. Okay, so let me go over the modeling part. So first we have some physical assumption. So we assume that on the material are linear. That is, the magnetic field D and the magnetizing field H are collinear. So you have this relationship, and usually mu is called the magnetic permeability. Second assumption is that we assume that the free current is negligible. So by ampere law, you have curve H equal to 0. And so you can write H as gradient of some scalar magnetic potential phi. Okay. So we can write H as something like this. And we will use this scalar magnetic potential in our equation later. We also assume that the particle exhibit rigid body motion and also have no slippery condition. So by rigid body motion, then you have the rate of strain du equal to 0. Here u is the velocity of the fluid, and we have rate of strain of the velocity is 0 inside the particle. Okay. We also assume that the flow is governed by Stokes law, and we have the fluid. The fluid is incompressible. Okay. So finally, we assume that the magnetic field acts on the fluid flow, but not vice versa for simplicity. Okay. So if the amalgam is well mixed, then we can consider the problem in the context of periodic homogenization. So in the context of periodic homogenization, we introduce a small scale epsilon here, and then we assume that on the particle is periodically distributed inside the domain omega epsilon, and here you have a reference cell. So here is the particle, which we denote by ys, and the outside is the fluid part. Okay, so let's come to the equation. So the first equation is the electrostatic equation. The innermost is the ampere law, and the middle one is the linear relationship between our material, and the outermost is come from the fact that we don't have any magnetic monopoles. Okay. So this equation is come with a normal boundary condition here, where K is a divergent-free vector field, which is defined on domain omega. Okay, so here we have the boundary condition on the boundary omega, but K is actually defined on omega. Next, we have the conservation of momentum. Okay. So on the left-hand side, this guy is the Cauchy stress tensor, which is defined by this formula. And T is the Maxwell stress tensor and is defined by this formula. So as you can see on the equation is written in dimensionless form, because here we only care about homogenization. And on the right-hand side, you have J, and you can view J as the resistivity. So next we have the equation of rigid body motion, du epsilon equal to 0 inside the solid part. So because of this one, you can rewrite u epsilon equal of ui plus ri across s minus ci. Here ci is the center of its particle. We see the translational velocity, and ci is the rotational velocity. So in order to solve equation 5, you need two more constraints. So those two constraints you need, and actually those one are the Newton third law, and they are a constraint to solve for ui and r. Okay. So let me mention the physical meaning of equation 6a. So actually 6a, you can view it as the balance equation between the hydrodynamic and the magnetic force, right? Because those four are the internal force for the combined fluid particle system. So those four cannot alter the total momentum, but only produce the exchange of momentum between the fluid and the particle. So we have the same argument hold for the top. So that's why we have equation 6b. Okay, so now put the thing together. putting together, we have this equation. Here you have U epsilon, P epsilon, and phi epsilon, a solution of the system. Okay, and then the homogeneous. Sorry, I think I. Okay, so the homogenization question is that what happened when we let epsilon go to 0? And so this section is answer in our first theorem. So if you let epsilon go to 0, then we have the homogeneous solution phi naught belong to this space, and the homogeneous velocity u naught belong to this space, and we also have the homogeneous pressure belong to this first space, where u naught, phi naught, u naught, and pi naught is the solution of the system. So on the coefficient mu effective, A and S are constant tensor, and okay. Sorry, but one slide is missing here. I don't know why. Let me open my slide again. Sorry about that. Okay. Yeah. Okay, so the coefficient here, mu effective is defined by this formula. So here you have omega k is the solution of this cell problem, and we can solve that mu effective is actually symmetric and positive definite. And next we have A, the four rank tensor A is defined by this formula, where you have chi ij is the solution of this cell stock problem. A is corresponding to the effective viscosity, and we can also prove that A is symmetric and strongly elliptic. The last constant tensor B is defined by this integral, where you have Cij is the solution of this cell coupling problem. So here you see that tau is the cell mass stress tensor. So this system captures the coupling mechanism between the fluid flow and the magnetic field. So after we prove that our phi naught, u naught, and pi naught is the solution of the homogeneous system, then we can apply some relativity result by Gianquinta and Matajaji, Huyen and Demajer and Demajer. So we can conclude that phi naught is actually differentiable. U naught is also belong to C1, and pi naught is continuous. Of course, you have pi naught is defined up to a constant because it's the pressure. So now if we let phi1 as in the formula, Then phi 1 approximates the oscillation of the magnetic equation. So therefore, we can expect that we have some strong conversion of the gradient of phi epsilon, because here the gradient of phi 1, which is mapped to y, we can be understood as the corrector of the macroscopic gradient phi naught. Okay, so we have that's why we have the strong conversion in L2 of gradient of phi epsilon to this guy. And if we put U1 as in this formula, then you have similar conversion. Okay. Okay, so now let me go over the strategy of our proof. So our proof employed the notion of two-scale conversion. So two-scale conversion was introduced by Thuyen and others. The main point of this conversion is to capture the oscillation of the sequence by introducing another small-scale variable y. In fact, if you test the sequence V epsilon by a highly oscillating function psi, then this interval will converge to the average of the product two function. So by density, you can extend this function space into some two function like this one or this one. The most useful properties of this notion is that everybody set in L2 is pre-compact in the topology of two-scale conversion. So let's come to the proof of our theorem. So the first step, we introduce the variational formulation. So first, we introduce the admissible space U epsilon. Okay, so of course we can show that U epsilon is actually a Hilbert space, and then equation 7 we can rewrite at the variational formulation here, where you have E1 and E2 those energy functional. Okay. Okay, so in order to solve the existence of the fluid velocity here, you need some regularity for the mass stress tensor. That's why we need to adopt a result from Fock-Gloria and Lopez-Tamay. So if we will adopt their proof, then we have some improved estimates for the gradient of phi epsilon. So basically, this lemma said that the gradient of phi epsilon is bounded by the norm of the field K. So now you can apply last theorem. You have the existence and uniqueness of magnetic potential phi epsilon, and also the uniqueness, existence and uniqueness of the velocity of U epsilon. Next, in order to solve the existence of the pressure P epsilon, we need to use the Lagrange-Molinier theorem. Okay, so here L202 is the space of L2 function with zero mean. So from the proof of existence and uniqueness, we also obtain some Rayleigh estimates here. And because the constant C here doesn't depend on epsilon, so you can extract some convergence of sequence. Okay. So you have the limit phi epsilon belong to this space, phi 1 belong to this space, and U0, U1, and also phi 0, such that you have all of those conversions. Okay. So those conversions are the crucial part of our proof. So if you choose suitable test function for those conversions, then you will obtain the following two-scale problem. Okay. Okay. So the question is how can we pick the right test function? Right? So the right test function has to mimic the oscillation that we want to capture. So for example, if you want to derive this first equation here, then because you have the formal asymptotic phi epsilon is approximated by phi naught plus epsilon times phi 1. So you will choose some test function has the form tau naught s plus epsilon times tau 1 S over S. Okay, so if you use this state function and combine with this guy, and then you plug back into okay, and then you will use the energy functional here, right? Then you will obtain our first equation right here. Okay. So another thing I want to mention is that if you look at this system, then it's a two-scale problem, because here we implicitly assume that the slow variable s and the fast variable y are independent. So somehow we lose the information given by y equal s over epsilon, right? Or equivalently, we lose the information that y can oscillate widely. So to retrieve the right information, the right oscillation that corresponding to the original system, you need to postulate some ancestors for U1 and you need to postulate ancestors for U1 and phi1. Okay. So those ancestors as follow. Okay. So you know that the ancestor for B naught, you need to introduce this one pi naught, because you want to capture the macroscopic behavior of the pressure, while in the magnetic scalar potential and the velocity, you don't have to introduce some phi naught or u naught, because you already have it in the conversion here. Right? You already have the macroscopic behavior. You already have the macroscopic behavior here, right? So you don't need to introduce it in the ancestors. So now you substitute all the ancestors into the two-scale problem. You obtain the effective equation in our theorem. Okay. So in the future, we want to extend our result into the case that we have strong coupling. That means you have the fluid can also change the magnetic field. We also want to consider our problem where the flow is governed by the Stokes equation. Another phenomenon we want to capture is the strain structure of ferrofluid. So because here, when you apply the magnetic field, then the particle in the fluid will form some chains like this one. And this is not true in the context of periodic homogenization. So we want to capture this chain structure, so we need to introduce some interaction functional between particles. And the last thing we want to do is to consider our problem in the context of stochastic homogenization, because obviously you don't have all the particle is distributed periodically inside the fluid domain. Okay. So my talk is over, and thank you for your attention.
Thank you very much, Thuyen.